If you've used a computer in the past, if you're in cybersecurity, you've probably used this thing called a virtual machine. Now, I use a variety of virtualization technologies, one of them being VirtualBox, right? A virtual machine is a very easy way for you to run code, download code in a contained environment, right? In theory, with the right isolation, if I download a piece of malware and put it into my VirtualBox, if it tries to do something evil, it's contained. It can't access my real files. It's not running really on my native operating system. And because of that, I feel happy and safe. Until we found out about 3 vulnerabilities in VMware's ESXi, another virtualization technology that allows malware potentially to escape. Guys, we're talking about these bugs today because, in my opinion, the future of the cybersecurity exploit landscape is going to lean heavier and heavier in these kinds of exploits, right? Ones that allow malware to come out of a virtualization technology. The reason being, as compute is moving more and more into the cloud, it is more and more important for attackers to be able to escape out of their containment onto the cloud native hosts and use that to spy on the tenants that are inside of the cloud architecture, especially in the world of AI cloud compute. Now we're going to do a breakdown of what virtualization technology is, what a hypervisor is, and exactly how these bugs manifest. I want to kind of read off the 2 major bugs that I think are pretty scary. So these apply to anything that VMware, now Broadcom, comes out with, right? So this affects vCenter or ESXi, including VMware Cloud Foundation, vSphere, and VMware Telco Cloud Infrastructure. Guys, if you're using Broadcom technology, you need to update your software. The 2 main ones that stick out for me are a critical out-of-bounds write vulnerability and a critical out-of-bounds read vulnerability in ESX, specifically in the VMXNet 3 virtual network adapter, guys. These are the bugs that are truly the bee's knees in the world of hypervisor escape exploitation, right? Now, I'm sure you're asking, maybe you're just a regular old cybersecurity practitioner, analyst, right? What's so bad about an out-of-bounds read? What's so bad about an out-of-bounds write? And why does this matter for hackers? Who cares if they can read and write? With all these big hacks going on and the over-encroachment of big tech, one concern that everyone has is privacy. And that's why today's video is sponsored by Proton. Proton is a no-brainer sponsor for the channel because they are concerned with one thing and one thing only: privacy. With their 2 flagship features, Proton Mail and Proton Drive, your data stays encrypted in a way that even Proton can't read it. What makes Proton Mail different is that your email is encrypted at rest. Proton uses end-to-end encryption to ensure that even if your email is stored in Proton servers, they can't read it. The password you use to log into your Proton account is used as a key that unwraps an asymmetric private key on their servers. They never can see your emails. And the same thing applies to Drive. The files on Drive are encrypted at rest. Proton literally cannot open these emails without your password, which they don't have. What makes Proton even better is they're very transparent on their revenue models and the way that they fund their company. Proton is a very rare tech company that has managed to achieve scale, but today does not have any venture capital investors. They are wholly user subsidized. This is like SaaS 101, right? They offer a good paid product to subsidize their free product without selling you targeted ads. Novel idea. Guys, the best way to help the channel out is to go use my link right here, go.lowleveltv/Proton, and go sign up for Proton free right now. Get 5 gigabytes of storage. And guys, you also get end-to-end encryption by default without paying. And if you want to use it for your business, get the paid plan. Thank you for sponsoring the video, Proton. Let's get back to it. Well, let's dive into exactly how this works. Now, the world of hypervisor exploitation is fairly complicated, but I'm going to break it down in simple terms. Okay, I'm going to keep it easy peasy for you guys, right? To understand hypervisor exploitation, we got to kind of understand what a hypervisor is, right? So if you consider that all code runs on a CPU, you know, that's the whole story. Computers run computer code, that's it. No, inside of the CPU that your native OS runs on, right? So right now we have host, right? The host is maybe Windows OS, right? The native host is running on top of the CPU, and the CPU exposes a variety of technologies. Like maybe it exposes AVX 512, right? The ability to do very, very large multiplication. Maybe it has an FPU, the ability to do floating point math, and it has like high precision floating point math. Well, one of the features that modern CPUs also have is this thing called VMX. VMX, what we call it in the Intel world. In AMD world, it's called SVM. VMX are virtual machine extensions, and SVM is secure virtual machine, I believe. I'm not an AMD guy. The native host is being exposed to the ability to run code in the context of a virtualized environment. What a virtualized environment means is we are given all of the RAM, right? The RAM is here, and this is all of the memory, right? And in the world of RAM, we have kind of two main addressing modes, right? We have physical, which is like literally just an index into all of the bits of the RAM. And then we have virtual, where there are translations made that tell us exactly what locations are able to be used and by what permissions and at what offset, right? So we have the program we're running is convinced that it has access to all the memory range, and it's 804A000, right? And because there are multiple page table entries for this, it is given the illusion that actually all three programs have access to the same virtual address, but this is actually, it's given the illusion that it has access to the same physical address, where in actuality, this is actually a virtual address, right? This is the idea of virtual memory. Now, what we're actually doing here is we have this thing that is called a system virtual address, an SVA, and then we have a system physical address, an SPA, right? This all is in the context of one operating system, right? This is all just Windows. What we can do is, because we are given the ability to have this VMX extension, another piece of technology enters the table. It's called the SLAT, the second layer address table, which allows us to translate then virtual addresses of the system into physical addresses of the host, right? So now we have another set of smaller addresses that the guest operating system, so now you have like maybe this is Linux on top of Windows. Now there is another translation layer that it translates this to a virtual address, right? And so when the guest is running, it is actually running all of its instructions natively on the CPU, but it is in a virtualized mode. What that means is every memory access does actually two translations, right? We go from guest virtual to guest physical, and then we go guest physical to system virtual, and then system virtual down to system physical, right? And the reason this can happen is we have this SLAT, which is a translation table inside of memory. Inside of the CPU, it's happening almost instantly, right? And there are translation look-aside buffers that basically cache the result of this translation, and all of this constitutes virtualization. And so by doing this, what we get is just code that runs inside the VM, willy-nilly, and that's the end of the story, that's the exploit. No, just kidding. So the question is, like, how can that be exploited, right? What can go wrong in this scenario that allows a guest running code inside of a VM to escape outside of the VM? Well, your virtual machine needs the ability to read the disk. Your virtual machine needs the ability to touch the network. Your virtual machine needs the ability potentially to read the contents of the microphone that you've passed through over USB. All of these things constitute real devices that need to touch real hardware. And so whenever you're doing this kind of leveling down, you're going from the guest called an L1 into the host called an L0, there's some kind of code that has to run that does the transaction between the two. And so VMXNet, the vulnerable device we're talking about, is the driver that a Linux guest is given when it lives inside a VirtualBox. So you have this VMXNet driver that runs inside the VM. And what it's actually doing when it wants to send a packet, right? It wants to send data over the network. What it has to do is alert the hypervisor and say, hey, I've got data to send you. The way that this works is it rings what's called a doorbell, right? So the world of PCI devices, PCIe, you have this thing called the bar. The bar is the base address register. There may be multiple. There's bar 0 up to bar of n. And basically, this is just a memory location. It's a piece of memory that lives deep inside of the VM. Right? And so what happens when the VMXNet driver wants to write a packet to the network, what it's going to do is it puts all the data into a buffer. It says, okay, I've got my buffer of data ready. It points the PCI bar to that data buffer, and then it does this thing called ringing a doorbell, right? So the doorbell over here gets rung. It literally just writes data to that doorbell. And because that is a memory mapped IO address, it is an MMIO address, what happens there is that actually causes a fault on the host OS, right? This actually sends the host very temporarily into an error state. It throws a trap. And the host then needs to decode what caused this trap, what caused this error to occur. And what it notices is, oh, this error came from within the bar register of the VMXNet 3 address. And now what that means is I have to go process the data it gives me. All we're doing here is alerting the hypervisor that there is data to send. Very easy. Okay, again, how could this go wrong? Well, The VMXNet 3 code that is actually running natively on the host is just a userland process that runs inside of ESXi. I think it's literally like, it's called like VMware VMX, right? This is a user mode process on the host, and all that process now is doing is it's going to parse the data that came from the user or from the guest, right? That sounds well and good. Let's arbitrarily process data from the user. Okay, that is where the bugs arise, right? When the guest is trying to send data out of the network, ultimately, when it rings that doorbell, something on the host has to process that data. And in doing that, if there's a vulnerability in the way the data is processed, then bada bing, bada boom, we have a guest host escape, right? Because we can use that vulnerability on the host via the data in the guest to potentially control code inside of VMware VMX. And this is exactly what this vulnerability is, right? A critical out-of-bounds write vulnerability in the VMXNet 3 virtual network adapter. An attacker with local admin privileges inside a virtual machine, which is very common. If I run a VM on AWS right now, I get root, right? But there's still a hypervisor beneath me. Using VMXNet 3 can exploit the flaw to execute code on the ESX host, resulting in a virtual machine escape. And then similarly, an out-of-bounds read vulnerability in ESX allows an attacker to disclose information or cause a denial of service condition in the host process. Guys, the problem with a arbitrary read and arbitrary write is those two primitives pretty much bypass all modern exploit mitigations. So when an attacker is trying to use an arbitrary write, right, the ability to put data anywhere that it wants on the system, and the data is arbitrary and the location is arbitrary. It's called a write what where. There are a few mitigations in place that stop them from doing this, right? The major one is ASLR. That's address space layout randomization, okay? What ASLR is doing, particularly in the case of like VMware VSX, the load address of where the VMware VSX binary in memory is loaded to and the address of the stack and the heap are all randomized. The reason for this is if I have ASLR enabled and I want to do this arbitrary write vulnerability, right? I want to write critically out of bounds. The question then becomes, where the F do I write, right? Where do I put my evil data? Well, if I also have an arbitrary read vulnerability, I can leak data out of the process that can give me hints as to the layout of the address space, defeating the randomization, which can then tell me where to write things. And then once I have this write figured out, right, I can do things like maybe a GOT overwrite. The GOT is a global offset table. What this is like, for example, when I call the printf function, okay? If I call printf, I didn't write printf. Intermediately, there is a linking process where it links printf against libc. The address of the libc printf is stored in this GOT table. If I can overwrite GOT with my own stuff, I can point it to evil code, right? Assuming I have the ability to mark it as executable. And bada bing, bada boom, I can get code execution this way, right? I'm obviously hand waving a lot of the nitty gritty of like doing ROP potentially and like getting to mprotect and marking a page as executable. People tend to really get caught up in the world of hypervisor exploitation and like, oh my God, it's like this black magic, like crazy stuff. It's really not that crazy. The hard part of hypervisor escape exploitation is figuring out where are the levers that the host processes code as controlled by the guest, right? And it always ends up being these major exploits that come out, especially with VMware. We have PCI devices that are virtual. They are virtual because they are emulated inside of the host, and the emulation, like anything, is just code, and that code can have vulnerabilities. Guys, if you are using VMware in any case, please upgrade. I think they're good software. You know, it's kind of like the de facto go-to. It's like what you have: VirtualBox, VMware ESXi, VMware Sphere, vSphere, and then Azure, which is Hyper-V, right? So like this is one of the three. Please update. Guys, the reason that I'm not actually showing you the escape, by the way, is like these are just the primitives. I don't know exactly where the bug is in VMware VMX. I could do a patch diff on that, but that's probably too deep for this video. Also, I think exploiting that and like writing a fully fledged VMware escape exploit would be like unethical. Just landing the primitive of the arbitrary read, arbitrary write is very complicated, right? And once you land those, you then have to actually chain them together. This is like the thing that Mythos is very good at, by the way, supposedly, to land a fully fledged exploit, right? So that being said, if you like this, let me know, and then we'll see you in the next one. I hope it wasn't too deep. If it was too deep, bit of a pretty deep dive today. If you like these deeper deep dives, do me a favor, hit that like button, hit subscribe, let me know in the comments, and then go check out this other video that I did about a similar VMware vEscape. I'll see it in their attention, but I hope it was good. I enjoy doing it like this.